In this video, we're going to talk about angles, lines, and parts of a circle. A radius is a segment that connects the center of a circle to a point on the circle. In this circle, O is the center of the circle, and R is a point on the circle, so OR would be an example of a radius of the circle. A chord is a segment that connects 2 points on a circle. So for example, A and Q are both points on the circle. So the segment connecting them, AQ, would be a chord. A and B are also points on the circle. So the segment connecting those 2 points would also be a chord. And finally, M and N are both points on the circle. So the segment connecting them would be a chord. MN is not only a chord, but it's a special kind of chord that passes through the center of the circle, known as a diameter. A diameter is double the radius because a radius is halfway across the circle, whereas a diameter is the full way across the circle. A secant line to a circle is a line that intersects the circle at 2 points. An example of a secant line in this picture would be L2, because L2 intersects the circle at points A and B at 2 points. L1 would be a tangent line to circle O, because it only intersects the circle at 1 point, at point T. A tangent line intersects the circle at just 1 point. And I'll just name this L1. I could have named this one L2. And since the tangent line intersects the circle at just 1 point, it looks like it's outside the circle because it just touches the circle at that one intersection point. A major arc is an arc or a part of the curved part of the circle, the part of the circle's circumference that measures more than halfway across around the circle, so more than 180 degrees. So, for example, if I go from M to Q this way, that arc would be a major arc because it's more than halfway around the circle. It's more than 180 degrees, so it's a major arc. So if I just write arc MQ, then actually it refers to the minor arc connecting M and Q. The arc that I just drew in pink that's less than halfway across the circle, that's less than 180 degrees. So if I just write MQ, that actually refers to the minor arc. It's the shortest path when you just see 2 letters. So for the major arc, if I want to indicate that I want to go the other direction, if I want to go clockwise from M to Q instead of counterclockwise, then I have to put a 3rd letter to indicate that I'm going in that direction. So I'll just put T in between. And that means I'm going from M to Q, but I'm going in the direction that T is in. And finally, a semicircle is half of a circle. So a semicircle here would be arc MN. Doesn't matter which direction you go in. If I went in this direction, it would be the same thing. A semicircle because it's halfway around the circle, measuring 180 degrees, half of the full 360. A central angle is an angle in a circle that has its vertex on the center of the circle. So here's my center of the circle O, and this angle has its vertex on the circle. So angle RON would be an example of a central angle in the circle. And last, we have inscribed angle. An inscribed angle is an angle where the vertex is on the circumference of the circle, as well as the other 2 points that touch the circle. So I'll give you an example. Angle QAB is an inscribed angle. Notice how its vertex is on the circle. And if we follow the rays of the angle, it also touches the circle. So 3 points on the circle, including the vertex. So I'm going to put that here. Angle QAB is an inscribed angle. Now, central angles and inscribed angles do have special relationships with the arcs of the circle, and we're going to talk about that a little bit as we go on in the video. One important thing to remember before we move on from here has to do with the radius that we were talking about at the beginning. We only had one radius drawn into the circle here. The only one here is, oh, no, there's more. There's not just RO, because MO would be a radius, because it's half of the diameter. And ON would be a radius, because it's half of the diameter. So something important to keep in mind about the radius, or radii of a circle, is that all radii of the same circle of a circle are congruent. They all have the same measurement. So in this picture, radius OR, radius MO, and radius ON would all have the same measurement, whatever that would be. We saw what the central angle was before. A central angle is an angle whose vertex is on the center of the circle. So if you take a look at the example on the left, that's a central angle because the vertex is on the center of the circle, right here on the center. In the middle, we also have a central angle, it's just facing a different direction, but the vertex is once again on the center of the circle. The last picture on the right is not a central angle because the vertex is not on the center of the circle. Central angles have an important relationship with their intercepted arc. When I say intercepted arc, I'm going to put that here, I mean the arc the angle opens up to or touches. I'm going to put that in parentheses, or touches. So for example, if I take a look at the first image on the left, for this central angle, if I follow the rays of the angle and see where they land, then that tells me what the intercepted arc would be. So the intercepted arc for the central angle on the left would be the arc that I just traced over in brown along the circumference of the circle. For the middle one, if I follow the rays of the angle down to the endpoints, where the endpoints touch is the intercepted arc for that angle. So central angles do have an important relationship with their intercepted arcs. Central angles are equal in measure to their intercepted arcs. So I'm going to put that here. Central angles are equal in measure to their intercepted arcs. So if this central angle was 50 degrees, its intercepted arc would also be 50. If this central angle was 30 degrees, then the intercepted arc would also be 30 degrees as well. A little bit more about inscribed angles, because they also have a special relationship with the intercepted arc. An inscribed angle is half of its intercepted arc. So if you take a look in this image, let's say the intercepted arc, the arc that the angle was touching was 100, then that means the inscribed angle would be 50 degrees. The inscribed angle is half of the intercepted arc. Now let's do some practice questions using the properties that we saw in this video. So for each of these, I do highly recommend that you pause the video and try your best to pick an answer before you see the work and the answer to see if you could do it yourself. And then you can always unpause the video to see the answer. We have circle O in the picture below, and the measurement of angle ABC is 24 degrees. We're looking for the measurement of angle AOC. So we're looking for this measurement here. The angle that we were given, angle ABC, is an inscribed angle. The vertex of the angle is on the circle, as well as the points where the ray ends. So we have 3 points on the circle, and that makes it an inscribed angle. And if I look at where the angle is touching the circle, that tells me where the intercepted arc is for that inscribed angle. So the intercepted arc for inscribed angle ABC is arc AC that I just highlighted in green. Using the fact that inscribed angles are half of their intercepted arc, I know that to get the intercepted arc, I need to double the inscribed angle. So I need to do 24 times 2, and that gives me 48 degrees. I'm looking for angle AOC. Angle AOC has its vertex on the center of the circle. So angle AOC is a central angle. And if I follow the rays to where they land on the circle, I see that the intercepted arc for angle AOC is also arc AC that I just highlighted in purple. Central angles are equal to their intercepted arcs. So if the intercepted arc is 48, the central angle is 48 degrees as well. In the diagram below, we have inscribed angle ABC. And what we're looking for is the ratio of the measure of angle ABC to the measure of the arc, AC. So if I just highlight inscribed angle ABC, I see that one of the rays hits the circle at A, the other ray hits the circle at C. So the intercepted arc for angle ABC would be arc AC, which I just highlighted in green. Remember that inscribed angles are half of their intercepted arc. So for example, if the arc is 100, the inscribed angle is going to be 50 degrees. It says the ratio of the measure of the angle to the arc. So it's a 1:2 ratio because the angle's smaller, so that's the one part, and double it is the arc. The angle is half of the arc. The arc is double the angle. In the next example over here, we are told that we have a diameter of the circle, segment AOB, and that's important because the diameter splits a circle in half. So that tells us that halfway across the circle is 180 degrees, and we know for sure the circle split in half because the diameter goes through the center of the circle. And we also know the other way around the circle, from A to B, is also 180 degrees. And that might be helpful later. I don't know if it's going to be, but I'm going to put it here. We are looking for arc BC, for the measurement of arc BC. So I'm going to highlight that. Arc BC, and I'm going to do that in brown, is this piece of the 180. So in order to figure out what that is, I first need to find arc AC. If I highlight the inscribed angle that we're given, the inscribed angle's endpoints hit the circle at A and C. So AC is the intercepted arc for inscribed angle ABC. And inscribed angles are half of their intercepted arcs. So if the inscribed angle is 28, the arc is going to be double that, which would be 56. So now we know halfway around the circle is 180, and we know arc AC is 56. So in order to find arc BC, we just need to do 180 minus 56 and see what's left over. And that's 124 degrees. So 124 degrees, and then that totals 180 when you add it with the 56. We do have another theorem involving inscribed angles that comes up a lot, and we're going to see some examples that use it afterwards, so I'm putting it here. Inscribed angles that intercept the same arc are congruent. So if we have two inscribed angles that intercept the same arc, the inscribed angles are congruent to each other. If you take a look at this picture, and first, if we look at angle ZYW, it hits the circle at points Z and W, so its intercepted arc is ZW. And if we take a look at angle WXZ, I'm going to highlight that one in brown. It also hits the circle at Z and W, so its intercepted arc is also ZW. Since inscribed angles are half of their intercepted arc, let's say the arc was 100. Since they're both inscribed angles that intercept the 100-degree arc, they would both be half of the arc, so they would both be 50, meaning that they're congruent. So that's a theorem that we have. If we have two inscribed angles that intercept the same arc, they are going to be congruent because they're both going to be half of the same arc. Let's take a look at this example over here, and feel free to pause the video so you can try it yourself and then unpause it to see the answer. In the diagram below of circle O, we have chords DF, DE, FG, and EG drawn such that the ratio of the measures of arc DF to the measure of arc FE to the measure of arc EG to the measure of arc GD is 5 to 2 to 1 to 7. So that's the ratio that each piece of the arc is in, and it's in order. So for example, they wrote arc DF first. So that's the 5 part of the ratio. They wrote arc FE second, so that's the 2 part of the ratio. They wrote arc EG third, so that's the 1 part of the ratio. And they wrote arc GD last, so that is the 7 part of the ratio. Identify one pair of inscribed angles that are congruent to each other and give their measure. So before we give the measurement and we find the measurement, let's first find two inscribed angles that would be congruent. And we know from our theorem before that if inscribed angles intercept the same arc, then the inscribed angles are congruent. So let's find two inscribed angles here that open up or intercept the same arc. The first inscribed angle I'm seeing is angle FDE. And angle FDE touches the circle at FE, so its intercepted arc is FE. The only other inscribed angle I'm seeing here is angle FGE. And notice how it hits the circle at F and E as well. So its intercepted arc is also FE. So angle FDE and angle FGE are going to be congruent to each other because they're inscribed angles that intercept the same arc. Now let's work on finding their measurements. So arc DF is here, arc FE is here, arc EG is here, and arc GD is here. So altogether, all the arcs that they gave us in the ratio before make the whole circumference of the circle, which is 360 degrees in total if we go the full way around the circle. So what I can do is I can make an equation that says if I take the 5x part and I take the 2x part, the 2 part of the ratio, I'm just representing it with an x next to it, and I take the 1 part of the ratio, and I take the 7 part of the ratio. Altogether, it should equal to 360 degrees. You can do this anytime you have a ratio. You can represent the parts of the ratio algebraically by putting an x next to each part, and then you can use it in an equation. Combining our like terms, that's 15x equals to 360. So now I'm just going to divide by 15. And I got 24, and that represents x. So 1x is 24. So 1x was EG, so that's 24 degrees. Now let me plug in to find the other pieces. Let me find the 2x part next. The 2x part was FE. So I'm going to do 24 times 2. That's 48. So FE is 48 degrees. And I'll do the 5x part next. That's DF. So 24 times 5, that's 120. And then finally, I'll do the 7x part, 24 times 7, and that's 168. And all of these, using our vocab from before, are minor arcs. They're all less than 180 degrees. So now that we know the measurement of arc FE, which is the arc that both inscribed angles intercept, we can find both of the inscribed angles because inscribed angles are half the intercepted arc. So if the arc is 48, half of that would be 24. So both of the inscribed angles, FDE and FGE, would both be 24 degrees. I'm going to put that here. They would both measure 24 degrees. If we take a look at this next example, we have chords AD and BC that intersect at E. When we have intersecting lines, I automatically always like to put in my vertical angles because we do have intersecting lines here. And it also says chords AB and CD are drawn. Which statement must always be true? Well, I don't know. So let me take a look at the picture again. I notice that we have inscribed angles here. One of the inscribed angles I see is angle ABC. And angle ABC hits the circle at A and C, so it intercepts arc AC. And I also see inscribed angle CDA. And that inscribed angle also hits the circle at AC, so its intercepted arc is also AC. So those angles would be congruent because inscribed angles that intercept the same arc are congruent to each other. So what I have here is I have the triangles are similar to each other. That's not an answer choice. Let's continue and see what else we can see here. Well, angle A and angle C are also inscribed angles that intercept the same arc as well. They both intercept arc BD. And another way that you can figure out that angle A is congruent to angle C is if you already have two pairs of congruent angles in the triangles, the third pair of angles also has to be congruent because there's only one measurement it could be to make the 180 degrees that a triangle needs to be. So answer choice 4 is the correct answer. It's the only one that I know for sure. I don't know anything about the segments at all, so I can't figure anything out about them. And angle B and angle C, careful, they are alternate interior angles, but we don't have parallel lines, so we don't know that they're congruent. Taking a look at this example over here, we have chords CT and BN that intersect at A. So intersecting lines, again, I'm going to put in my vertical angles. I always like to do that as soon as I see intersecting lines. We also have chords CB and NT drawn. Which statement is always true? Well, again, I see inscribed angles that intercept the same arc. CBN intercepts arc CN, as does NTC, also intercepts arc CN. So inscribed angles that intercept the same arc are congruent. Let me see if that's an answer choice. No, and already I see this is not correct because angle BAC is a vertical angle. It's not congruent to the inscribed angle. And I also see there's another pair of inscribed angles that intercept the same arc, arc BT. But you can also use the fact that if two pairs of angles in the triangle are congruent, the third pair also has to be congruent because there's only one value it could be to make 180 degrees. Let's see if that's an answer choice. Angle BCA, no. Angle NTA is the other inscribed angle. Be careful about answer choice 4. Those are alternate interior angles, but once again, we do not have parallel lines, so you do not know that they're congruent to each other. The last two answer choices are proportions, and that comes from similar triangles. And we do have similar triangles here because we do have congruent angles, right? We have actually 3 pairs of congruent angles. We have AAA, so it's super similar. The triangles are definitely similar to each other. So now we just have to see which proportion correctly puts corresponding parts together from the two triangles. Let's take a look at number 1. NT is from the triangle on the right. TA is also from the triangle on the right. So then I need 2 sides from the triangle on the left, and they need to correspond. So let me see, do NT and CB correspond? Yes, they do. They both are on the same spot on the 2 different triangles. And then do TA and BA correspond to each other? Yes, they do. So answer choice 1 is the correct answer. If you look at answer choice 3, there should be things that don't correspond there. Which relationship must be true? We have intersecting lines. It tells us that in the question. AD and BC intersect at E, so we once again have vertical angles. And we do have inscribed angles that intercept the same arc. Here's one set of them. CAD intercepts arc CD. And so does angle CBD. It also intercepts arc CD. So those are congruent to each other. So the triangles are similar. Here we have another example. In the diagram below, right triangle ABC is inscribed in the circle with a right angle at angle ABC. Explain why AC must be a diameter of the circle. So angle ABC is an inscribed angle. And notice if I highlight it, it touches A and C. So its intercepted arc is AC. That intercepts arc AC. Since inscribed angles are half their intercepted arcs, if angle ABC is 90 degrees, then arc AC is 180 degrees. Since arc AC is a semicircle, that means AC is a diameter. Any mention of that the arc is 180 degrees, so it's getting split in half the circle, so AC has to be the diameter because it's getting split in half. Anything of that would be great. And that's another theorem that we do have. Inscribed angles that intercept a semicircle, that intercept half a circle, that intercept a diameter are right angles, just like we saw here. We have a couple more examples for this video, 3 more examples. So if we take a look at the first one here, it tells us BC is the diameter of circle A. And it says that point D, which is unique, different from points B and C, is plotted on circle A. So I'm just going to plot it somewhere. It doesn't matter where. Which statement must always be true? Triangle BCD is a right triangle. Well, yeah, that does have to be true, right? Because angle BDC, wherever I put D, is an inscribed angle because D is on the circle as well as B and C. Inscribed angles are half of their intercepted arc, and no matter where I place D, the intercepted arc is going to be a semicircle, half of the circle, which is 180 degrees. So that means half of it's going to be 90 degrees. So that is always true. For number 2, we don't know anything about the side lengths because the sides are not radii of the circle, so we don't know anything about them. So we don't know its isosceles. Then it says BAD and CAD are similar triangles. We don't know anything about that. Wait, it says BAD and CBD. Oh, they can't be similar because CB, well, they could be similar, the big triangle and the small one, but we don't know another angle because I don't know if this is being split at 90 degrees. I don't know another angle, so I'm not sure if that's true from what we have here. And then BAD and CAD are congruent triangles. All we have is the reflexive property here. We don't really have anything else, so I can't say that about them. So the only one that you can definitively, without a doubt, know for sure is one. Triangle BCD is going to be a right triangle because there's going to be a right angle there. In circle M below, diameter AC is drawn, chords AB and BC are drawn, and radius MB is drawn. Which statement is not true? triangle ABC is a right triangle. Well, angle ABC is an inscribed angle, and it's an inscribed angle that does intercept a semicircle, which is 180 degrees. So that means this is going to be a 90-degree angle. So that is true. So that's not the answer choice we're looking for. Triangle ABM is isosceles. I don't really know that for sure. I'm going to come back to that because I don't really know that for sure. That could be the one we're looking for. I don't really have any reason to believe that. 3. Arc BC, so that's this arc over here, is equal to the measure of angle BMC. Angle BMC is a central angle. Its center is on the center of the circle M. So central angles are equal to their intercepted arcs. So that is true. And then arc AB, that's this arc over here, is equal to half the measurement of angle ACB. That's an inscribed angle. Inscribed angles are half the intercepted arc, not the other way around. So this would actually be the wrong answer over here. So be careful with that, because inscribed angles are half of the arc. The arc isn't half of the angle. And now I see what I misread with answer choice number 2. With answer choice number 2, it's asking about ABM, not the whole big triangle, ABM. And with triangle ABM, AM is a radius, as is BM. So it is isosceles. So the correct answer choice here, the one that's not for sure true, is answer choice number 4. And then finally, our last question for this video. In the diagram below, we have a bunch of chords of the circle. Line FDE is tangent to the circle at point D, and radius AO is drawn. Sam decides to apply this theorem to the diagram. An angle inscribed in a semicircle is a right angle. Which angle is Sam referring to? See if you could pause the video and find the inscribed angle that opens up to a semicircle, that opens up to a diameter. It's not angle AOB, that's a central angle. Let's see if it's BAC. Nope. That doesn't open up to a diameter. Let's see if it's DCB. There it is. Endpoints on the diameter, on the semicircle. So it intercepts the semicircle. And that's it for this video.